Hello and welcome back, everybody. Today in calculus, we look at the second part, the second section of chapter 11, which is on series. So before all of this, in the previous section, we talk about a sequence, where sequence is really just a function where the domain is going to be whole numbers, because it's going to be, whenever you talk about sequence, you're looking at a string of numbers that could or could not possibly have any patterns. So in today, we're going to be talking about a series, which we're going to define and how is it related to sequence. And to be a little bit more specific, we're going to look at something called a geometric series, which you probably heard of because it's from Algebra 2. And then there's the harmonic series, which, for you music people, you probably heard of because it's a terminology in music then. And also how to test a little bit further on convergence and divergence using limits, and also looking at these geometric and harmonic series, how they're basically related. So to begin with, let's go ahead and define what is a series then, okay? So the first things first is that if you have a series, which we denote as S of n, it is basically going to be the sum of all the previous terms of the sequence. So that is to say, if I have S of n, that's what I want to solve for, then that is supposed to be equal to the first term plus the second term plus the third term, all the way to the nth term. So that's pretty much, in short, the series then. It's the sum of all the terms leading up into the sequence. Now, the one type of series that we are interested in is the one called geometric series, which we need to kind of first define, because that's the one that's going to be interesting in calculus. In Algebra 2, you learned about the arithmetic sequence and also the arithmetic series, and those are, those are pretty nice for the most parts. But again, the geometric one is where all the stuff from calculus is going to be useful. So the next thing is, let's go ahead and define a geometric sequence then. Now remember, a sequence is basically kind of like a string of numbers with patterns. So to be a little bit more specific here, if I tell you that you have a geometric sequence, you're basically going to have a sequence where each term is a ratio of the last. So then that means, if I were to write it out, here is an example of a geometric sequence then. A of n is going to be equal to, how about, let's say 4, and then 8, and then 16, and 32, and so on, and so on, and so on. So note what's happening is that I'm basically multiplying consistently by 2 in order to get from one term to the next. Or maybe if I have something like, say, A of n is equal to, how about, let's say, 100, and then we have 50 negative, and then we have 25, and then we have negative 12.5, and then positive 6.25, and so on, and so on, and so on. That right there is also a geometric sequence, because again, you're multiplying consistently in order to get from one term to the next. And in this case, that multiplier is going to be negative 1/2. Now, the first one, it doesn't look like we're going to have too much to, play with, because as the sequence goes along, the number gets bigger and bigger and bigger. But it's really the second one that I'm really interested in, because if you notice how this plays out in terms of a series, what if I asked you to sum up all the terms? Or what if I asked you to sum up like some of the terms? And in this case, you might actually get some sort of finite value, and that's what I'm interested in for right now, okay? So then when it comes to a geometric series, then what that means is I want you to sum up all of those terms then. So in this case, if we were to once again look at A of n being this sequence right here, and by the way, we can probably write an equation for this. A of n, the sequence, is going to be, if you remember correctly from Algebra 2, is supposed to be the first term multiplied by r, the ratio, to the power of n minus 1. Or some people write, in this case, it's going to be A of 1 because it's the first term. So that it means that my A of n in this case is going to be equal to 100 multiplied by negative 1/2 raised to the power of n minus 1. And that's going to be my geometric sequence equation. Now, as I said, what I'm interested in is maybe something like, say, S of 7. How do you solve for the sum of the first 7 terms? So in this case, I'm asking for, like, say, 100 minus 50, and then plus 25, and then minus 12.5, and then plus 6.25, and then minus, let's see, that's going to be 3.125, and then plus 1, 2, 3, 4, 5, 6, and then one more. Let's see how good my math is. 1.5, 6, 0.25, I think it is. But basically, yeah, I want to know how to add them all up without having to use a calculator. And we know that in this case, it does add up to be something because it's finite. So the question is, well, how do we add them all up? And also, this is probably something that's pretty simple because I could just go ahead and add them all up like numerically. But what if I asked you to add up like, say, the first 100 terms? And that's where it gets a little bit more complex. So our first question to ask is, how do you find the sum of a geometric series? How do you find the sum of a geometric series? So once again, this was something that was derived a while back in Algebra 2, but for the sake of refreshing, let's go ahead and talk about that. So here's what I want. I want to find out that if you have a series, if you have an A of n, which is a geometric sequence, and that is going to be A of 1 multiplied by r to the n minus 1, I want to know what S of n is going to be, which is supposedly going to be the sum of the nth terms. So if I were to kind of write it out according to my equation, then that's going to be A of 1 plus A of 1 times r plus A of 1 times r squared plus A of 1 times r cubed, and then plus so on and so on and so on, all the way to the last term, which is A of 1 multiplied by r to the n minus 1, because that's going to be our last term according to the equation. The question is, what is this equal to? Is there like a simple equation that I can kind of work off of? Well, in order to derive this, I'm going to take a different approach from what the textbook actually normally uses, because, after a while I get kind of, sick of using the same proof over and over again. I wanted to use something a little bit different. So here we go. Let's do the following then, okay? Let me do this. Let me go ahead and take out the, actually, you know what? Nah, let's just go ahead and leave it in. Let's just, because we're good at algebra, or we need practice in algebra. Here's what we're going to do. We're going to go ahead and do the following. I'm going to go ahead and use the Punnett square, I think that's what it's called, to multiply out something for us, and just so that we can do a derivation here. I'm going to go ahead and take the first part, which is going to be my series right here. So the first term is A of 1, and then second term is A of 1 times r, and then the second term, the third term is A of 1 times r squared, and then after that is A of 1 times r to the third, and A of 1 times r to the fourth, and so on and so on and so on, all the way to the last term, which in this case is going to be, once again, A of 1 times r to the n minus 1. So you can see right here, that is basically what I'm trying to solve for. Now, what I'm going to do is I'm going to take that series right there, and I'm going to multiply it by 1 minus r. Okay, I'm going to multiply it by 1 minus r. So you can see how the Punnett square works, because in each of the square, I'm going to go ahead and put the result of what you're supposed to get after you FOIL all this out. So here we go. In the first part, you have A of 1 times 1, which is going to be A of 1. Then the second piece is going to be A of 1 times r. Then we have A of 1 times r squared. You have A of 1 times r to the third, A of 1 times r to the fourth, and so on, all the way to the last term over here, which is A of 1 times r to the n minus 1. Now, the second row, we're going to go ahead and multiply that out. In this case, we're going to get negative A of 1 times r. The second part, we'll get negative A of 1 times r squared. The third part, we get negative A of 1 times r to the third, negative A of 1 times r to the fourth, negative A of 1 times r to the fifth, and so on, all the way to the last one, which is going to be negative A of 1 multiplied by r to the n, because r times r to the n minus 1 is supposed to be r to the n. Now, the sum of all of these squares will then give you the result of these two multiplied together. And if you notice, now here's the fun part, or here's the neat part of this, is that there are a lot of terms that actually cancels out, because even though we have a lot of squares, if you look carefully, this guy right here cancels out with this guy right here, because it's the same thing. In addition, then this guy right here is the same as this guy right here. And then the next part, this guy right here is the same thing as this guy right here. And then the next one, they're going to cancel out also. And then they're going to also always going to symmetrically cancel out diagonally in this case, all the way into the last upper right-hand corner. That's going to cancel out with what's over here. In short, what I'm saying is all that's left over is really just the first term over here and the last term that's over here. So in short, what that means is if I take my series, which I'm trying to solve for, a of 1 times, a of 1 plus a of 1 times r, plus a of 1 times r squared, plus a of 1 times r to the third, plus all the way to a of 1 times r to the n minus 1. I took that and multiplied by 1 minus r. The result is supposed to be equal to a of 1 minus a of 1 times r to the n, because that's what's left according to my lattice or Punnett square. And since this is what I'm trying to solve for, then I'm going to go ahead and divide both sides by this part. So then that means my equation that I'm trying to solve for, this thing right here, is going to be equal to, and this guy looks like it's factorable. Let me go ahead and factor it out. The first term multiplied by 1 minus r to the n divided by 1 minus r. And there you go. That's going to be our derivation of the geometric series equation then. Okay. All right. So now let's go ahead and then apply it. So then that way we can see how that actually works out. So here is an example, and then we can go ahead and do a few more after that. For the series right here, 100 minus 50 plus 25 minus 12.5, and so on and so on and so on. I want to find out what is S of 10. And remember, S of 10 means I want to find out the sum of the first 10 terms. Well, simply put, we're just going to have to throw it into the geometric series equation, and we're pretty much good to go. In our geometric series equation, we denote that a of 1, the first term, is equal to 100. R, in this case, is the ratio, which is equal to negative 1/2. And n, how many terms we have, is equal to 10. So putting it all together, the answer is of 10 is going to be equal to 100 multiplied by 1 minus, and here you have to be careful, negative 1/2 in parentheses raised to the 10th power. And then all of that divided by 1 minus in parentheses 1/2. So take all that and put it into a calculator and see what you get. So let me go ahead and quickly do that right now. So 100 multiplied by 1 and then minus 0.5 raised to the 10th power, and then divided by, looks like it's 1.5. So on the calculator, it's showing up to be roughly approximately 66.602. Okay, so that's going to be the sum of the first 10 terms. Okay, so that's not too bad. Now, if this goes on forever, though, the question is, well, what happens then? Because if you notice, the numerically, your numbers, each term is getting smaller and smaller. So that means that it's almost like you're adding 0 in the very end. And when you're adding a whole bunch of terms where eventually it's going to be 0, you're going to eventually get to some sort of finite number. If I were to look at the number line, here's what's happening. First, it's say here's 0. I'm going to go over to the right to 100. And then I am going to move over to the left by subtracting 50. And then afterwards, I'm going to move to the right by 25. And then I'm going to move back to the left by 12.5, and so on and so on and so on. So in terms of like what's happening, you're basically kind of like oscillating back and forth, and it definitely looks like it's going to converge towards somewhere. The question is, where is that somewhere on the number line? And it definitely looks like it's somewhere between 0 to 100. Now, right now, I have an answer that is 66.6202, which I do believe is very close to that number that I'm looking for. So the question is, well, what is that finite number if you were to add up all of the terms? Well, in this case, then, we're going to have to go a little bit further and figure out how that actually works out. So here, if we were to, actually, before I go on to the next part, let's go ahead and maybe solve for it right now. What I'm trying to solve for is the following then, and just applying some calculus to it. I want to know what happens as limit as n approaches towards infinity of S of n, the series. Well, plugging in my numerical values of each one, then that means that you're supposed to get the following. Limit as n approaches towards infinity of 100 multiplied by 1 minus negative 1/2 raised to the nth power, and then divided by 1 minus negative 1/2. So this is just using the geometric series equation. And remember, what I want to do is I want to look at what happens as n approaches towards infinity. Now, as n approaches towards infinity, the interesting term is actually going to be this guy over here, because if you have a fraction, if you have any number between negative 1 and 1, exclusive of negative 1 and 1, of course, raised to a really, really big exponent, the result is that this is really going to go towards 0. So all that is left is just my 100 divided by 1 plus 0.5. So that is equal to 100 divided by 1 over 0.5, which I do believe comes out to be 66 and 2/3. So that right there is going to be my sum of the series if I can somehow manage to add up all the terms. And that is definitely pretty close to what we have. So in terms of like, trying to come up with a general formula, well, that's what we're going to talk about in this next part over here. For a geometric series S of n, where its geometric sequence is denoted as A of n is equal to A of 1, let me sneak that 1 into there, A of 1 times r to the n minus 1, if your ratio, the term that you're multiplying in order to get from 1 to the next, is between -1 and 1, so if the absolute value of r is going to be less than 1, then I'm going to say that the series converges according to what we just did as a problem. And then in terms of what it converges to, well, looking at our equation, we said A of 1 multiplied by 1 minus r to the n divided by 1 minus r. This guy is going to go to 0 because n is going to infinity with a ratio that is between -1 and 1. So all that's left is A of 1 divided by 1 minus r. So that means it converges to, more specifically, the first term divided by 1 minus r. So that's the convergence numerical value. But whereas if your ratio is greater than or equal to 1, then S of n diverges, because in that case, you're basically adding a whole bunch of big numbers or you're subtracting a whole bunch of big numbers, and it's not going to go anywhere, right? So if you have something like, say, 1 minus 2 plus 4 minus 8 plus 16 and so on, you can see how the numbers are progressively getting bigger and bigger. And even though it's multiplied by negative, it is basically getting bigger and bigger without bounds. So therefore, it's going to be divergent. And then if it's divergent, we just pretty much say it's done then. Okay. So that was the conclusion of all the stuff that you learned back in Algebra 2. All right. So now let's go ahead and see how that works out, just to kind of refresh your memory once again. So here in this first problem is I want to find out what is this guy going to be equal to. For each of these problems, I want to determine if the following are convergent or divergent. If convergent, then find out the sum. So this is what is known as a repeating fraction, and you've seen it before in the past, probably in like 7th grade or 8th grade or whatever. If I were to write it out, this is the same thing as saying 0.529292929 and so on and so on and so on. I want to know what is it equal to, meaning like, is it equal to some sort of finite fraction that we can actually have? And the answer is yes, it actually does equal to a finite fraction. So we're going to figure out what that is. Now, we wrote out what this is equal to if we expand it. But more importantly, if you notice, what we have right here is actually a geometric series. And here, if I were to write it this way, you'll probably be able to see that. 0.5 plus 0.029 plus 0.00029 plus 0.0000029 and so on and so on and so on. So, if you basically disregard the 0.5 right now and look at the second part and on, you can see that that's your geometric series. Looking at the numerical part that we need, we know that the first term in this case, A of 1, is supposed to be equal to 0.029. Whereas the ratio is supposed to be 0.01 because you are multiplying by 1 over 100 in order to get from one term to the next. Well, that satisfies all of our conditions where your ratio is supposed to be between -1 and 1, and you have infinite number of terms. So therefore, that is going to be convergent. And in terms of what it converges to, it's going to be the first term, which is 0.029 divided by 1 minus the ratio, so 1 minus 0.01. And don't forget the 0.5 that's been sitting on the side the entire time because you have to add that too. So if we take this and simplify it, that's 0.5 plus 0.029 divided by 0.99. Let's go ahead and move some decimal places over. So 0.5, we can just go ahead and leave that part. Plus the other part will be 29 over 990. And I guess we can go ahead and combine those two together if you wanted to. So that is equal to 495 over 990 plus 29 over 990. So in the very end, it comes out to be, how good my math is, 400, it's not even 400 anymore. It's like 500 something, right? Let's see, that's going to be 4 over here. Carry the 1, so that's going to be 2, and that's 5. So 524 divided by 990. I tell you guys all the time that The higher up you go in math, the suckier you become in lower math, like algebra or even arithmetic. All right, so there you go. That's number one then. Okay. Now, for the second one, let's do the same thing. I want to find out if this is convergent or divergent. And if you look at what we have, once again, it's really a geometric series because you have the summation and you have to figure out where the R is going to be. Now, if you can't see it, maybe the best thing I can do is probably divide through so you can actually see that then. So here, if I were to divide through, you're going to get, let's see, the summation from 1 to infinity. It's going to be 10 multiplied by 3 over 5 to the n. And then plus, for the other part, it's going to be summation of n is equal to 1 all the way to infinity of 15 multiplied by 2 divided by 5 to the n. And I can do that because they're both raised to the nth power for each of the exponents. Well, there it is. That is going to be the geometric series for each one of these. And now we can see what's going to happen then. Now, this part, this is where you have to be very, very careful because, yes, the convergence calls for a of 1 divided by 1 minus r. And remember that a of 1 represents the first term, okay? So in this case, the difference between our equation and the equation that we normally have for a geometric sequence is that this is a of 1 times r to the n minus 1. But regardless, a of 1 is always going to be the first term. So what I'm telling you is, yes, it is still convergent because of your ratio being less than 1, or your absolute value of ratio is less than 1. But your first term, now this is where you're going to have to plug in n is equal to 1 to get the first term. It's going to be 10 multiplied by 3/5 divided by 1 minus 3/5. That's going to be your first term in the first one. And then for the second one, you're going to plug in 1 into n because that's your first term. So that's 15 times 2/5 divided by 1 minus 2/5 then. So we clean that up, and that's going to be our answer in this case. So that looks like on top, let's see, the 10 divided by 5, that's equal to 2 times 3, so that's 6. Divided by the bottom part, which looks like it's going to be 2/5. And then plus, for this part, 15 divided by 5, that's equal to 3. So that's also equal to 6. And then divided by 3/5 over here. So if I multiply everything by 5 to both top and bottom of all of this, then hopefully we can get something that's a little bit nicer. So in the first one, that is going to be 30 divided by 2, and then plus the second part, which is going to be 30 divided by 3. So that looks like it's 15 plus 10. So the answer is going to be equal to 25. Okay. All right. Now for something that's a little bit more complex, and this is actually now getting closer and closer to our calculus portion of the sequence and series. I want to know, according to what we just learned right here, for what values of x will 1 plus x squared plus x cubed plus so on all the way to x to the n converges. Okay, I want to know what it converges to if possible. Now, if you want, you can write this out as a summation, which is the following. The summation of n is equal to 0 all the way into infinity of x to the nth power. Or if you want, you can start at the n is equal to 1 for the first term to infinity of x to the n minus 1. So either one of those will be acceptable as a summation. One starts at 0, the other one starts at 1. Make sure you make that modification in the exponent just in case. But anyhow, the question is, well, what does this converges to? Here you can see that it's a geometric series because you're multiplying by x in order to get from one term to the next. Now, using my geometric series equation, then what that means is that this guy right here, if it were to converge, then that means it converges to the following. This is going to be equal to the first term divided by 1 minus the ratio. That's equal to x. So then that means that, hey, you know what? These two things are supposedly identical to each other then, numerically. But if you think about it a little bit further, well, that's not always going to be true because depending on what x is, you might or might not get that answer, okay? So here's what I mean, for example, okay? Let's go ahead and take this guy and plug in some values of x just to see does it or does not work because, you know, this seems a little sketchy. If x is equal to 0, then that means that you would have 1 plus a whole bunch of 0, and that's going to equal to 1 divided by 1 minus 0, so that equals to 1. So yeah, that actually works out. If x is equal to, let's say, 2 in this case, now this is where it gets a little hairy because then you get 1 plus 2 plus 4 plus 8 and so on and so on, so on, all the way to the nth power. And that's supposed to be equal to 1 over 1 minus 2. Now, there's no way that something on the left right there, adding up all of those positive terms, will give you a negative number, which is equal to negative 1. So the question is, well, for what value of x are these two equations the same thing? Well, this is where you have to keep in mind that in the geometric series, you have to make sure that your ratio has to be between negative 1 and 1. So our ratio in this case is supposed to be x. So then that means the only time that these two equations are equal to each other is going to be when the absolute value of x is less than 1. And if you're, trying to kind of wrap that around your head, let's look at it graphically over here. Okay, so if you go to Desmos, you'll notice that I basically graphed the first equation, which is going to be the expansion right there, 1 plus x squared plus x to the third, and so on, so on, so on. I made it to go up to over 9,000 terms because, well, over 9,000 is a thing supposedly. And that's pretty close to infinity at this point. Then underneath it, you'll notice that I have the equation 1 over 1 minus x, which I did not graph yet. And I'm going to go ahead and graph it right now and watch what happens. You can see that as soon as it graph, wherever the graph is, these two are going to be almost identical to each other. There it is. I just have to kind of switch the screen. You can see that these two graphs are almost identical to each other, only in certain values of x. Everywhere else is going to be different. And that place where they're going to be the same is going to be between negative 1 to 1, because outside of negative 1 to 1, the two equations are going to be different. So that's the cool thing, because what I have done is basically I have taken an equation, right, a rational equation, and wrote it as a polynomial. And that's really nice because now if I'm thinking about it from a calculus perspective, I can do a lot more with the polynomial than I can do with the rational expression in terms of, like, say, derivative and antiderivative and all that other stuff. Okay, so the important takeaway of all of this is the following over here. Now, this is the part that is going to be very, very essential. Okay, if you have a series that's going to converge, then we have to say that the limit as a of n, the sequence, is going to go towards 0. Meaning that, if your series is going to add up to be a certain number, the terms that you're adding are getting smaller and smaller and smaller and smaller, and that's eventually equal to 0. Is it the true case with the other way around, meaning that if you have a bunch of terms that are getting closer and closer to 0, does the series converge? The answer is actually no, and we'll see why is that true then in that case, or why is that not working in the converse. And then the next piece that we need to take away is that if the limit as n approaches towards infinity of the sequence does not equal to 0, then the series right there is going to be divergent. So to give you, like, say, an example of this, just to kind of write it out, let's say I want to take the summation from n is equal to 1 all the way to infinity of n over n plus 1. You'll notice that for this part right here, as n approaches towards infinity, that is getting closer and closer to 1, right? The limit as n approaches towards infinity of n over n plus 1 is equal to 1. And what that means is you're basically adding a whole bunch of terms that are getting closer and closer to 1. And so they're not diminishing. So therefore, you're just adding a bunch of 1. So therefore, it diverges because there are infinitely many number of those terms then. Okay, so you have to make sure that the limit goes to actually 0 for it to converge. So here is the next part. This is the one that is kind of like showing you the converse of why that first statement isn't actually true. Okay, if you have a series in this case, which is known as the harmonic series, right? And again, I mentioned this at the very beginning for those of you guys that are music people. Let's say that you have this harmonic series, the summation of 1 over n. I want to know, does it converge or diverge? Because if I were to write it out, this is what it looks like. The summation of n is equal to 1 all the way to infinity of 1 over n, that's like saying 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, and so on and so on and so on, and it goes to infinity. At first glance, you're thinking, okay, well, this probably can converge And the reason is, well, it is going towards 0. Each term is getting smaller and smaller and smaller. But it turns out that it actually does not converge in this case. And here's the reason why, believe it or not. Okay. Here, what I'm going to do is I'm going to group each term, and you can see what's happening. The 1, I'm just going to group it by itself. And then the 2, now I'm going to group that also by itself. The next part is I'm going to group the 1/3 and the 1/4. Now that right there, if you add it together, that is approximately equal to 0.583, and it goes on forever. And that number right there is definitely going to be greater than 1/2, right? So this part right here is going to be greater than 1/2. Then if I group the next batch right here from 1/5 to 1/8 and I add that up, that is equal to 0.635 in this case. And you can see that that's also going to be greater than 1/2. You can kind of get the idea as to what I'm going to do. The next part, I'll probably group the fractions that are going to go from 1/9 all the way to 1/16 and add them together. And believe it or not, that is equal to 0.663. And that right there, that is going to be greater than 1/2. And so what's happening is I'm basically clustering a whole bunch of terms together, which if I add them together, they're always going to be greater than 1/2. So the question is, once again, does this converge or diverge? Well, if all of those terms are going to be greater than 1/2, then that means that what I can compare it to is the following. This is going to be greater than 1 plus the first group, plus 1/2, plus the second group, that's 1/2, plus the third group, that's 1/2, plus the fourth group, that's 1/2. So this guy right here, that is going to be this 1/2. This guy right here, that's going to be this 1/2. This guy right here, that's going to be this 1/2. This guy right here, that's going to be this 1/2. And if you look at what I'm comparing it to, since you have infinitely many number of 1/2s, because remember, this goes on forever, since this guy right here, that is below it, that's going to diverge because you're adding up a whole bunch of terms that are not equal to 0. Because, you can see 1 plus 1/2 infinitely many number of times, that's going to go towards infinity. So if you have a series underneath that is going to diverge, then therefore the series that is going to be above it, because it's greater than, is also going to be divergent as well. Remember, this is what we call the comparison test back in the last section. Okay? All right. So in conclusion, the summation of n is equal to 1 to infinity of 1/n is going to be divergent then. Okay? All right. Now, here's the very, very last one then. It seems like we've been here forever, but we're almost done. All right, I want to know if this last one right here is going to be divergent or convergent. Well, in this case, we are going to have to do a little bit something that, we're going to have to strategize this for this one right here. Because if you look at what we have, this is definitely not geometric. You're not multiplying something consistently in order to get from one term to the next. So the question is, well, what do you do? Now, hopefully, if you look at this form right here, you might recognize that this is something that we can change into a partial fraction. Now, if I were to write this out, this is what we have then. 1 over 2 times 1 plus 1 over 3 times 2 plus 1 over 4 times 3 plus 1 over 5 times 4, and so on and so on and so on. That definitely looks like it's going towards 0 if you take the nth term. But then the question is, what does it add up to be then in this case? Okay. So what I want to do is I want to take a look at this guy right here, and maybe we can rewrite it so you can see it a little bit better. This, if I were to write it using partial fraction, here we go. So 1 over n times n minus 1 is equal to a over n plus b divided by n minus 1. Multiply everything by the denominator, so n times n minus 1. So we get 1 is equal to a times n minus 1 plus b multiplied by n. So let n equal to 1, and that will give me b is equal to 1. Let n equal to 0, so that will give me a is equal to 1. So what that means is what we have comes out to be the following. The summation of n is equal to 2 of all the way to infinity of 1 over n minus, let's see, oh, I'm sorry, I kind of messed up in this case. If n is equal to 0, then that means that a is equal to -1. I too apologize for that one. So what we have actually is going to be -1 over n, and then plus 1 over n minus 1. And you're thinking to yourself, okay, well, I split into partial fraction, but it looks like I made it more difficult. But here is what that looks like then, if I were to kind of write out a few terms, just like I did over here. So let's see, the first term, if I plug in, that's going to be -2. So that's going to be 1 over 2 negative. And then it's just going to be +1. Then the next term after that is going to be -1/3. And then that's going to be plus, what is it in this case? It's going to be 1/2. And then afterwards, it's going to be -1/4. And then we have plus 1/3. And then after that, we're going to have -1/5, and then we have plus 1/4, and so on and so on and so on. And now if you look carefully, there are actually a lot of terms that cancel out, because if you remember from the lattice thing, this is that same idea. Here we have -1/2, here we have +1/2. Here we have -1/3, then we have over here +1/3. Then next we have -1/4, and then we have +1/4. And it goes on forever. So in the very end, you're basically going to go to the last term, which is going to be 1 over n minus 1. And as n approaches towards infinity, that last term is pretty much equal to 0. So all that is left is just this beautiful 1 at the very beginning. So that is basically what it's going to converge to. All right, so definitely this is a long video. So, hopefully you took some pauses and, go out and get a drink. But now it's finally over. All right, thank you so much for watching. I will see you later. Okay, goodbye.